In normal distribution, we will also face the same issue as we did with other distributions, where what if one of the parameters is missing? What if the mean is missing? What if the standard deviation is missing? What do we do in that case? We actually follow something called the standardization. Sometimes some books actually explain how to compute normal distribution through standardization first, and then through the process that we did. But I only like to use standardization when necessary, which is when we're missing parameters. So what do we mean by standardization? So because normal distribution is a naturally occurring thing and it could happen um, in natural circumstances, sometimes I'd want to compare two different distributions, or sometimes I want to compute the area below a curve without having to deal with different numbers every single time. As you've noticed, that no matter what your mean and standard deviation is, the area between the first standard deviations and the second standard deviation will always be standard. They're always the same. So why not standardize that with a more an easier to deal with mean and standard deviation in order for us to easily and visually visualize how to compute the distributions. So the capital letter Z is used for the standard normal distribution. This standard normal distribution follows a normal distribution, and it has a mean of 0 and a standard deviation of 1. Now, no need to write 1 squared because the square root is just going to be a 1 here. So it follows a mean of 0 and standard deviation of 1, and this is what the graph will typically look like. So if I have any normal distribution, I can standardize it to look like this. So the equivalence of 1,010 would be 0, and the equivalence of 1,030 would be positive 1, and so on. Now, most real-life random variables are do not have a mean of 0 and standard deviation of 1. However, it's possible to transform them to look like standard normal distribution. So if I have a random value here of, let's say, 1,023, I want to know what's the equivalence value here. What's the equivalence value in the standard normal distribution? And then I can nicely compute some typical values of the standard normal distribution here. So this process of converting a variable x to z is called standardization. And again, the value you get from standardizing is called the z-score. How do we compute this? How do we actually standardize? How do I shift from this version 1023 to the standardized version? We use this formula. We take the x value that you have, we subtract from it the mean of your original mean, and we divide it the whole thing by the standard deviation. So this is the Z transformation. The value you get tells you, so this Z value you get will tell you how far you are from the mean. So for example, if I did this 1023 and say it gave me a Z score or a Z value of 0.7, it means I'm 0.7 to the right of the mean. If I take 0.9, if I take 990 and I standardize it, it will give me -1, which tells me that I'm -1 away from the mean, so it means I'm to the left of the mean. So we will compute these z-scores, and we typically, as mentioned before, it's helpful when you have two different distributions and you want to compare them, so it's easier to standardize both of them and then make a comparison. And we will mainly use it if the mean and standard deviation are missing and required by the question. So before we actually compute missing means and standard deviation, I just want to make sure and emphasize that you understand that the transformation will give you the equivalent area below the curve. So this exercise is just to help you visualize the understanding. It's not something we'll ask you to do typically, but it's just to help you visualize what's happening. So given that x follows a normal distribution of 10 and standard deviation of 2, I want you to find the probability that x is less than 13, bigger than 9, and between 9.1 and 10.3. So how do I want you to do that? I want you to compute the probability of x being less than 13 normally using normal CDF, and then from negative infinity to 13. Compute this value, see what you get. Once you've computed this value, so using the x follows the normal distribution, I now want you to follow the z distribution with a mean of 0 and standard deviation of 1, which means I want to know what's the equivalence of 13 in the standard normal distribution. Well, I need to use the formula to know what it would look like. So the equivalence of 13 in the standard normal distribution is 13 minus 10 over 2. So that will give me 3 over 2. So the equivalence of 13 in the normal distribution graph is 3 over 2, which means if I compute x less than 13, it should give me the same value as if I computed z less than 3 over 2. This has a mean of 10 and standard deviation of 2, and this has a mean of 0 and standard deviation of 1, but they should give me the same answer. So let's just have a look. So normal CDF with negative infinity to 13, with 10 and 2 as my standard, my mean and standard deviation, I get 0.933. Once I standardize 13 to 3 over 2, and I computed the same thing, I also get the same answer. So again, I'm trying to get you to visualize that it is the same thing. It's in the same position in the graph. It's the same area because of the way that normal distribution behaves. But we like to use standardization because you get to deal with smaller numbers. So using this, now that you've seen how it's done for this, can you try it out for B and C before I reveal the answers? So for bigger than 9, same thing, but this time the standardization is negative 1 over 3. So you can expect on the graph we're looking at somewhere here and negative 1 over 2. So I'm looking at the area above this, which is not a coincidence because if we graph the x distribution, if this is 10 and I'm looking for the area above 9, and in the z distribution I have 0, it means I should be below here, and I'm computing the area above. And both of them will give me the same answer. This time it's 9 to infinity or negative 0.5 to infinity. And if I'm between two values, you standardize both of them. So it's from negative 9 over 20 to 3 over 20. And again, notice when I put those two values with their respective mean and standard deviation, I get the same answer. So now that hopefully you're convinced that it works the same, how is it useful? So let's see how standardization is useful here. Pause and read the question. Try to see how the information is organized here. So in here we know that the mean is 5, but we don't know the standard deviation. I just have information that if the mass is bigger than 5.2, then it's the 10% of the bags that weigh 5.2, which means that less than 5.2 would be 0.9. Now, why am I doing less than? Sometimes it's just easier to deal with. I don't have to worry about the tails, right tail or left tail. So how do I solve this? How do I find this m? Well, what if I standardize this? I don't know the mean, the standard deviation here. But if I can standardize 5.2, so convert it to somewhere in z, well, what's nice about z is that I know the z's mean and standard deviation. So what if I convert this to standard normal and then use those values? So what is the equivalence of 5.2? It's 5.2 minus 5 over sigma, which is 0.2 over sigma. Keep this as an unknown, so 0.2 over sigma, this is what we're going to use. So now what does it look like in the formula? Now that I'm in the standardized world, I'm looking for the probability that z is less than 0.2 over sigma. In the previous examples, we actually had the number. Now we just have it as an expression, which is fine. But I know that less than this is 0.9. Where's the 0.9 from? It's from here. So we've converted the m to the z, we've converted the 5.2 to 0.2 over sigma, and we know that it's equal to 0.9. We know that the areas will still be the same if I convert it to standardize. So go back to, well, how do I find a missing value if I know the area? We use inverse norm. So we're going to use steps that we already know. But this time we know the standard deviation and the the mean, so I can use it to actually find the value of z. So this is the value of 0.2 over sigma. And then when I equate them with each other, I can then rearrange to solve and find sigma. So this is how we find missing parameters. Now, what if two things are missing? What if the mean and standard deviation are missing? You need two pieces of information to create two simultaneous equations and then solve them however you need to. So again, I would encourage you to pause and try this on your own. So in this question, I'm just going to rewrite this. Again, it's much easier to deal with this as a less than. So this would be 0.95. And I already have the p less than 25, which gives me 0.1. I want to standardize these so it's easier to deal with. So 85 minus the mean over sigma is my first, let's call it Z1 value. And then Z2 value would be 25 minus the mean over sigma. And then we do the inverse norm. So I know that if Z is less than, this time not 85, if it's less than Z1, it should be equal to 0.95. And I know that if Z right now is less than Z2, it will be equal to 0.1. And then we do the inverse norm of these, and I get that Z1, I compute what Z1 is, so on the calculator, and it will give me that Z1 is 1.64485 equals to 85 minus mu over sigma. And in here, Z2 is negative 1.28155 equals to 25 minus mu over sigma. So you have two unknowns, two equations. You can solve them however you want to. You can rearrange them to make them look like a system of equations and then use the simultaneous function on your calculator. You can algebraically do them if you want to. I'm not going to go through how to solve these simultaneously in detail, but I'll just show you the quick method that I use. I just made sigma. I just multiplied by sigma on both sides. And then I moved the mean to the other side. So then I had a system of, in terms of where sigma and the mean were on one side. And then I canceled out the mean. That's one method to use. Eventually, I was able to find the standard deviation first, which gave me 20.5. And then using, so here I'll just say use simultaneous, any simultaneous method. And then using the 20.5, I substituted in either, so either in this formula or this formula, and then I got the mean as 51.3. And since you have a calculator, I would encourage you to substitute those values and double check that, yes, the probability of x bigger than 85 is 0.05 and less than 25 is 0.1. So hopefully this process of standardization is easy to interpret and use. It's useful for these things when things are missing, and comparisons also. These are some questions you could do. This is a helpful exercise to have a look at, is when the absolute value is written in there. I just want to remind you how absolute values work. So if you have absolute value of something, then it means that it's less than y or bigger than negative y. So you just need to rewrite this in this notation, just to remind you of that. And then you can practice some of these and read through this description also.